Hello everyone. Today, I will share information on retaining wall modeling in the SDA program. First, when we open the retaining wall tab here, we are presented with a screen like this. On this screen, we initially encounter console type, retaining wall structures. If there is such a retaining wall, you will solve it from here. If you have a Britannic wall, then you can select the option below. Here, you can choose your material as either stone or concrete. Alternatively, as shown here, we have the pit wall option. If you have a retaining structure like this instead of that type, then you can model it using this option. Besides that, we have our settings section here. From the settings section, you can adjust the language, and after modeling the retaining structure, it allows us to analyze and export drawings in DXF format. You can select the DXF format here. In addition, we have a help option available here. First of all, you can get information from here before starting the retaining wall module. If you click on the help section, a PDF file will open, and you can obtain information about the use of the program through this PDF file. I will examine the console type, retaining structures, specifically the option labeled retaining wall, here in this video. Then I will briefly mention pit wall at the end and conclude my video. Now, when we click on the retaining wall option here, the console type retaining wall appears on the screen. As you can see, there are dimensions here. We can play with the dimensions. We can change the dimensions from this section. We can also select our wall width. Here, we define the wall and ground properties. We input the seismic effects that occur here. If we have a dynamic load, we enter those as well. Here, we input the unit volume of concrete. Here, we discuss the material strengths of iron and concrete. Also, take a look at our overturn center section. You do not need to enter any points here. When you do not enter any points, the program calculates for a lot of points by itself. It determines whether there is any sliding here, and for different center points. However, if you are asked to look at a specific point, you can enter the coordinates of the relevant point here to check the top 10 overturn center. So you can check the overturn center. Generally, the program does this when you do not enter a point. Sliding surfaces are drawn considering different centers. Of course, these are considered as the actual overturn center point that provides the most unfavorable safety ratio. In other words, we are looking for the most unfavorable point here. But as I mentioned, you can also delve into any point you are curious about and examine the result there. I will also leave the calculations of the program here. I will not directly enter any point myself. Now, of course, if you want to open a new project, you can access these options from here. You can save your operations here from the load section. You can also call up a project you are currently working on and continue with the operations. We have an options section. When you click on the options section, yes, look here. You can adjust both your static and design options. You can select the reinforcement spacing and reinforcement diameters used here in the design section. In the static section, our 2018 regulation is currently selected, and here you can see our safety factors. Here, for example, we have the wall evaluation safety under seismic loading, and we take the coefficient as 1.3. According to the regulations, what is actually mentioned here is as follows. For example, here we have an active soil load. This soil load is trying to overturn the retaining structure. The retaining wall resists this, for instance, with its own weight. It resists here due to the force created by its own weight, and the friction effect it generates on the surface. We are calculating the moments that attempt to overturn it. We calculate the moments created by opposing forces. Here, the ratio of the moment created by the opposing forces to the moment created by the forces attempting to overturn must be at least 1.3 times. In other words, the safety factor that our director is referring to can be explained in this way. Besides that, here you can see our load combinations. If you want, you can add different combinations and also view the resulting situations. Yes, here, you can arrange these options according to whichever regulation you want. Of course, you can save this as a default setting or change it specifically for this project. Here, if you want the 2007 regulation, you need to click on that, and then click on this, like this. Yes, we say to consider it according to the selected code. Right now, it has been considered according to the 2007 regulation. We are saying to change this for this project. So if we want to keep it as the 2007 regulation, we can do it this way. But if we want the default value to remain as the 2007 regulation in all projects we enter, then we need to click this. This is because the safety factors in the 2007 regulation are different. Accordingly, it is taken into account. Right now, I have brought it back to 2018. These are our options. Additionally, you can use passive loads here if you want. But if you don't use them, you will stay on the safer side. Because passive loads are the effect of the soil here. The soil here is holding the retaining wall. In other words, it counteracts the overturning effect created by this active earth load. Here, a passive load is formed. If you do not take this into account, you will end up making calculations that are on the safer side. Here, we have the option to optimize. When we click on the Optimize option, it shows us this. Let me explain right away. Yes, at first glance, we have a lot of options here. Here we have the height of the wall. Similarly, we have the thickness of the foundation. Besides that, look here, we have our tooth optimization. This is important. We have options related to tooth optimization and, of course, our base width here. Now, when examined, you can also have the program automatically optimize these. Or when you change these values yourself, how does the optimization of the dimensions here work? Have I changed these dimensions to be economical? Or is an inadequate section being formed? Or is such a structure unfeasible? Or is it a previously mentioned method? Accordingly, you can derive more suitable retaining wall sections that will also reduce costs. Here, in the first option mentioned initially, he talks about the foundation width. Here we have the difference section. The difference section shows us the distances in between. Look, it goes with a difference of 0.4 and 0.5, meaning it varies by 0.1. In the horizontal part, it also varies by 0.25. This is shown here as well. So, what are these values? Since we are examining the optimization of the foundation width here, the situation being referred to is actually our current value of 4.5. Here we actually have our value of approximately 4.5 with a length of 0.8. So, this wall actually shows us the distance from the beginning of the foundation. It is actually optimizing these values. So right now, I have a value of 4.5 here. Let's say I want to take this as 4. What kind of result will I get when I take it as 4? We will look at that now, and let's say I want to take this as 0.9 instead of 0.8, so here, I am marking the option that corresponds to 0.9 and 4. When I mark this, I can also select a different sound option. Here, as you can see, changes are actually occurring in the relevant dimensions on this three-dimensional shape shown in the figure. Let me revert it to its original state. Yes, this is what I want right now. And to implement this, in the project, I am checking the Assign to Wall option. This will assign these dimensions to the wall as well. As can be seen right now, I need to create a model like this. There is no problem. The light is green, so it means okay here. It means you can do this. So, here, you can see the approximate costs. Look, when I do it this way, the cost will be around 12,134 TL. This way, you can visualize the cost. When I say Assign to All, look, it changed this to 4 and this to 0.9 by itself. In addition to this, as I mentioned here, we can optimize regarding the heel part. Or you could say the tooth, we can perform an optimization related to this. There. Look at this 0.7 heel height. Here, the distance to the heel is 3 meters. You can optimize that. You can optimize the thickness of the wall, which ranges from 0.9 to 0.25. Besides that, we have our foundation thickness here, which is crucial for stability and durability. At the end, when you come to the foundation thickness, yes, we have a thickness value of approximately 0.6 meters here. We have a value of approximately 0.3 meters here. You would perform an optimization on these two values to ensure efficiency. I want to make it 0.7 and 0.4, for example. I took this here, and when I clicked on Assign to Wall, as you can see, it changed these as well. But from here, of course, you can automatically select all the optimizations and also choose what you want. You can also perform automatic optimization. It is currently carrying out the optimization. According to that, it will adjust the dimensions. And finally, it will also display the cost for us. You can view how much profit you have made from here. The program will automatically perform the optimization for you. Yes, right now look. The fees are written here, so there has been a drop of more than half. At this moment, I performed an automatic optimization. Yes, I say OK here if you say Assign to All, and it will automatically assign this optimization result. Yes, I didn't take any action because I didn't want any optimization. If you want to do it, as I said, you can click on that option. Now, I would like to mention an important point here. It is not very possible to save your retaining wall under high earthquakes or high elevations. When you encounter such situations, you will see that when your earthquake increases to a certain extent, or when you have a larger heel height here, you need to make the wall height much larger. You will already notice that it is not sufficient. In such cases, I took 0.8, and even that is currently not sufficient. For small earthquakes, you can certainly manage this by adjusting the dimensions. However, when there are high earthquakes, very large landforms, you need to turn to shoring wall systems instead of constructing a retaining wall. Otherwise, you will not be able to save the structure. Related to the modeling of the retaining wall in such situations, what you need to do is turn to the shoring wall system. Besides that, look here, this heel section is very important. The heel section especially has a braking effect, provides control against shear effects from horizontal forces. There is also sliding control for retaining walls. In the horizontal direction, your heel has a very important function against this slipping. Therefore, the height of this heel needs to be at a certain value. Here, let's say that when I reduce this heel, meaning I have 0 heel, basically we have no heel. In that case, the likelihood of experiencing deficiencies high, it is beneficial to have some form of heel. Currently, this structure does not exhibit inadequacies, but different types of structures may show inadequacies. This is important. The support geometry should be understood. It's necessary not to deviate too much from this geometry. Here, a wall comes from this point, and there is a section on both sides. The foundation continues at certain widths on both the left and right. Placing the wall in the corner and constructing it from only one side is not a correct approach. In other words, the wall must have a certain distance from both sides. It needs to be positioned in between. It cannot be at one endpoint. Such geometries are not a correct approach. It is important that you do not go outside of this geometry. Besides that, look here, you are also adjusting the angle. With this value, the soil loads are currently coming in at a slope of 5 degrees. For example, you set the angle to 10, and you can see that there is a change observed. Here you can look at this from here. That's why, as I said, when your earthquake loads become excessive, if you increase the height here, we will see that it won't help. Yes, this is what I currently have to say regarding the retaining wall. Now that we have specified all the dimensions, we can move on to the analysis section. Of course, if we have groundwater here, we need to consider the groundwater level as well. I am currently assuming it should be present. Now, in order to analyze this, we first need to record it. Yes, if you press the save button. Yes, I will register a data here. Yes, MudData is currently registered, and here I am pressing the Analyze button. He is currently performing an analysis. Yes, he has finished the analysis and has immediately presented the results to me. Here are my element properties. In fact, I have wall properties, the selected properties found here. Here are my dimensions and the drawing. After that, the calculation section starts in detail. The loads shown here. Here you can see the active soil load. An analysis is being conducted under these loads. Yes, as a result, you can see that wall overturning and sliding checks are being performed here. Yes, after these are done, take a look there. An overturn center is determined. Based on this, a slope surface is drawn, followed by calculations made with a safety factor. This is calculated for both MudData, non-earthquake conditions. Here it shows that it was done under earthquake loading. We already went directly into the report here, but when we reach the analysis result, we also have reinforcements, etc. You can visualize these in the same way. Here you can also determine the overturn center. Look inside any point, you can check it yourself. For any points here, if you right-click, it will initially show the most unfavorable condition. In other cases, it will be larger anyway. The factor of safety section here is important. You can see that. These are already written here. A lot of schematic lines have been taken and it is written under the conditions that arise from them. Here in the design section, you can see that we have our reinforcement. It states the required area here as well, which is 8.4 square meters. Based on this, you can change the reinforcement selection yourself. Here, your quantity takeoff is also being done. This is important. We have the option of single reinforcement or double reinforcement here. You can specify these as you wish. Accordingly, your quantity takeoff will change somewhat. You can select these. These are important. Besides this, the report shows the reinforcement. After these have been provided, the given reinforcements are written here as a report. Here, I actually want to point out a specific aspect of the data entry. If you are going to apply an extra load, you can enter it yourself here. Let's say you will enter a vertical PV load or a horizontal pH load. You can divide these by the relevant wall width and treat it as a single dynamic load. You can also define an additional load. Let's talk about the natural wall properties here. We also had soil properties. These are important as well. The data pertaining to our soil is here. You need to enter. Let it be the specific weight of the liquid. Besides that, let our specific weight of the dry ground be. Of course, this part is very important. There is the friction angle of the ground surface here. We also have the shear resistance angle here. These are important factors. We need to enter them correctly. Here you also need to enter a value in the first option that is 2/3 of the value you entered here. There will always be a difference of 2/3 between them. The friction angle of the ground surface needs to be 2/3 of the shear resistance angle. These are important in this regard. Yes, you can enter the number of floors here in this way. Now, regarding the analysis results, yes, you can generate a report in this manner. As I mentioned, you can print the report as a PDF from here. If you are looking for something specific in the report, you can find it by typing its name here. You can zoom in out of the screen a bit here. Features like this are available. Yes, now we come to the drawing section. Here, in the drawing section, look here. Yes, it immediately creates the drawing. This is important. If you are in the editor section, you can make adjustments to the drawing. You will carry it here and you will delete it. These options will be active. You are in the first part and these options are available. You cannot do these actions. Here you can only view. Yes, right now. Yes, when you click here, it also thickens our wall here and makes the drawings accordingly. This is very important. When you click on our option at the very bottom, notice that it displays the screen. Here on a white background. If you close it, paper texture part. That is, when you create the paper texture, it shows up here in white. You close this. You can also get it in black like this. This is important from this perspective. Here, you can also make a choice. And as I mentioned, you can carry out the transportation. Yes, you need to select part here first. Let's say you will be moving these. After selecting them this way, you will say yes. Goods and yes. Where do you want to move this part? Accordingly, you can take it, move it to a different place from here. I mentioned this as an example and demonstrated it. Besides that, of course, you can save the drawing. Here you can save files in the DXF format and open them this way. Yes, this way he has also saved the drawings. Overall, these are my comments regarding the Provincial Art Correct modeling. Now, I will provide a brief overview of Pitfall modeling and conclude my video. Yes, now I will provide information about Pitfall modeling. Here, the structures are generally types of retaining walls used to hold the soil or ground in a short-term manner. There are various types of retaining structures. If you want to build a long-term retaining structure, then you should not use the Pitfall option. The data entries here are the same as those for console-type retaining structures. There is no change in the situation. Another point of difference is that there are two solution methods: a classical solution, finite element solution. Additionally, we can of course add stages here. These are the most fundamental differences. Unlike the retaining example I described earlier, which involved cantilever-type retaining structures, here it generally occurs as follows. Here, the foundation part sits here. Generally, the foundation of the relevant structure sits here. This wall section here actually represents the basement walls of the relevant structure. The foundation also sits here. The general logic is also like this in Pitfall structures. One of the important points here is that passive forces must definitely be taken into account. This part is very important. This must definitely be taken into account. We marked this for that reason. There is actually no step. If you want, you can also add a step this way. I would like to talk a little about the solution methods here. Classical solution operates as seen in the previous example of the retaining wall structure. Does not consider the ground as elastic at all. When we perform finite element analysis, determines point through iteration, and let's say that the part above this point behaves in a non-elastic and non-linear manner. It has determined a specific point on a pitfall. And from this particular alignment onward, the part above behaves non-elastically while the part below behaves elastically. And after making the determination, in this part here, the program models the portion of the rigid concrete structure below that line with elastic springs. And because it models with these elastic springs, the movement of the springs here balances the forces coming from the inelastic part above. In other words, all types of force calculations are accounted for. Therefore, there is no need to include any safety factors or anything like that here. All forces are directly addressed in this way. One of the most important differences here is this. However, if the point found through iteration, as I mentioned, appears at a lower level, meaning let's assume it appears at the very bottom, then it indicates that the structure is becoming less than fully elastic. It means that there is no more significant part in terms of elasticity. In that case, process is already being carried out like in classical solutions. There is no difference occurring there. Of course, in order to determine the point that will be elastic, and to place the elastic springs below it, the earthquake must be zero. The earthquake is not zero. This cannot be done. Now we can change the dimensions. Here, as we mentioned, just like in the previous model. First, I will create a solution according to the classical method. If there is a negative situation, it still comes out the same. Here, look, I am adding a step. For example, it is not saving right now. But when I do it without steps, it is currently saving. Now I am analyzing this. Yes, when I analyze it, look here. The analysis results are coming out again. And the necessary passive loads were also considered this time. Classical calculations are being performed. Yes, solves with the same logic, and here, the latest specifications also terminate. There is also an important situation regarding the reinforcements here you see. The engineer needs to input these themselves. These are reinforcements at 100 centimeters gaps. The reinforcements here are those coming from the superstructure. Therefore, the engineer needs to personally address these reinforcements that are highlighted in red. Besides that, there are reinforcements provided by the program related to this. For instance, it is placing a constructive reinforcement in this foundational part concerning the retaining wall. Here we already have our shear reinforcement. This type of reinforcement is being used. Similarly, we can also make a dual or triple selection. Here, the reinforcement. Drawing is done in the same way. Now we have stated the results. Like this, the report can be prepared in the same way. Similarly, drawings can be obtained in the same manner. Also, just like in the previous example, it follows the same logic. Look here, you can call the drawing and obtain it here. Yes, now I want to solve it using finite elements. I am analyzing here. Yes, the analysis is now complete. The main point I want to show here is that when it solves with finite elements, it identifies a specific point. If we zoom in a little more. Yes, the remaining part underneath here is taking it elastically, and look here, elastic springs are being loaded. The remaining part is considered as the inelastic part, and the movement of these elastic springs here is actually damped. Well, the logic here is based on that. Accordingly, the calculations are made. Yes, you see the first task here. Based on this logic, the calculations are also being carried out. Yes, these are my comments on our pitfall. Models, thank you for listening to me. I wish everyone good work.